Hello everyone, welcome to lecture on digital logic design. In this lecture, I will talk about programmable logic arrays. Programmable logic arrays are a type of combinational circuits, just like read-only memories, to implement Boolean functions, different Boolean functions. But programmable array can implement Boolean functions in a much better way than read-only memory and multiplexers. So let me revise what are read-only memory and how we can implement Boolean functions with read-only memory. Read-only memory are combination circuits which consist of a decoder and some OR gates depending on the number of outputs of the ROM. And there are fuses that can be broken if needed, and this task of breaking fuses is called programming ROM. So this is an example is a 32 cross 4 ROM, which consists of a 5 cross 34 decoder, and there are 4 OR gates which represent outputs. These OR gates, the number of OR gates can be increased if the number of bits of the outputs are increased. There is a problem. For example, if we have some Boolean functions where we have don't care conditions, then even if there are don't care condition, but they're relevant AND gates in the decoder are there. Even if they are not used, but the decoder have the OR gate, the AND gates for them. For example, this ROM gets a 5-bit input. There are 5 variables, and there is a decoder 5 cross 32 decoder. In this decoder, for the 5-bit input, this generates all possible minterms for the 5-bit input. If we have 5-bit input, then we have 2 raised to the power 5, which is 32. 32 minterms are generated. These are the minterms. So in this case, a 5 cross 32 decoder is used, and this decoder will generate 32 minterms. So if we are using this ROM to implement a Boolean function, let's suppose a 5-variable Boolean function, and if there are some don't care condition, for example, minterms 0 to 25 are used, but minterms 26 till 31 are not used. But still, this decoder produces them, even if they are not used. So this is a kind of wastage of resources. But programmable logic arrays can do better than ROM while implementing Boolean functions with don't care conditions. So let's talk about programmable logic array. This is a very general block diagram of a programmable logic array. This block diagram represents multiple logic arrays. So first, let me teach you what each block inside this programmable logic array represent. So we have n inputs and we have m outputs. There is a set of k product terms which are implemented with AND gates, and there is a set of OR terms or sum terms represented with or implemented with OR gates. This is similar to ROM. And ROM we had AND gates which were there in the decoder, and for those AND gates in the ROM there are product terms or AND gates in the PLA as well. There were OR gates in the ROM. There are sum terms or OR gates in the PLA. There are fuses in the PLA, and there are no fuses at the end of the ROM. The n inputs, there are n variables. Complemented form and normal form are given as input to these AND gates. So for example, if we have n inputs and we have k product terms or k AND gates, then n cross k links are for the complemented variables, and n cross k fuses or lengths are for the normal variables. Similarly, if there are k products and there are m sum terms or OR gates, then between these two blocks there are k cross m lengths which can be broken, which can be programmed. And for each output, if there are m output, then there are m fuses which can be used to either make the final output complemented or in normal form. So there are three group of fuses. One group is here for the inputs, one group is here for the product term and for the sixth sum term, and one group is here for the outputs. So this is a general block diagram of programmable logic array, and it is much easier to explain this by giving an example. So let me implement Boolean functions with programmable logic array, and we will design a programmable logic array for implementing these functions which are shown in the truth table. And then I will teach you in this lecture how to program a programmable logic array so that it would implement these Boolean functions. So for example, we have these two Boolean functions, three variable Boolean functions. The Boolean variables are a, b, and c, and the Boolean functions are f1, f2. So we have two Boolean functions, and each Boolean function is a three variable Boolean function. So I'm going to explain in detail how we can implement these two Boolean functions using a programmable logic array. To begin with, we have the first step, and in the first step we have to represent the Boolean functions in sum of product form. If there are multiple m Boolean functions, then we have to represent each of them in the sum of product form. Sum of product form is a standard form which include or represent a Boolean function in the simplified form. To represent a Boolean function in the sum of products form, then we can follow the classical approach of K-map representation, which would be used to represent Boolean function in the sum of product form. So we have two Boolean function, and we have to simplify these two Boolean function and represent them in the sum of product form. To begin with, let's start simplification of the Boolean function f1. This is a three variable Boolean function, so we can use a three variable K-map to simplify it. So this is a three variable K-map. We have the values for f1 here. So we can just map these values over to the K-map. 0, which is not represented there. For simplicity, just we write 1 so that we can just group them and simplify the Boolean functions. So the empty boxes represent 0, 0, 0, 0, 0, 1, 1, 0, 1. So this is the K-map for the function f1. Now we have to make groups. We can make two groups, each of two squares. This is the first group, this is the second group. We cannot make a single group of 3 because we cannot make a group of 3 squares. We cannot make a group of 5 squares. We cannot make a group of 6 squares, so on and so forth. So we can make two group of 2 squares. When we simplify it, we will get the Boolean function f1, which is equal to ab prime plus ac. ab prime for this group and ac for this group. So we simplified Boolean function f1, which is represented in the sum of product form, and this Boolean function now consists of two product terms. Similarly, let's simplify Boolean function f2. Just like f1, this Boolean function is a 3 variable Boolean function. So we can simply create 3 variable k-map for it and map the values over it and simplify it. After writing the values here over to the map, we get this map. The empty squares represent 0. So again, we can group them. This would be the these would be the groups, the two groups. Each group consists of 2 squares. And after we create product terms for these groups, we will get F2 is equal to AC plus BC. This is AC and the vertical group is BC. There is an A which is not visible, it is a typo, but there is an A here. So we have simplified Boolean function F2 and represented in the sum of product form. So we have completed the first step. We got the 2 Boolean functions in the sum of product form, which are there. Next, the next step of implementing Boolean functions with programmable logic array is to remove the redundant product terms from these set of product terms for F1 and F2. If there are any product term which is common in both functions, we have to remove it and keep just a single occurrence of it. So if we look at F1 and F2, we see that product term AC is common in both. So we will just remove the redundant product term and we'll keep it once. So we have these product terms AB prime, AC and BC. Even though AC is there 2 times, but we will keep it just once. So AB prime, AC and BC are the product terms. So we have the product terms for the m Boolean functions. In this case, we have 2 Boolean functions, so we got 3 product terms for these 2 functions. The number of product terms can be increased or can be decreased for the Boolean functions depending on the Boolean functions. When you simplify them, just remove the redundant product term and combine all the product terms into a set, and we would call them product terms. So we have 3 product terms in this example. So we got product terms. Next, create a programmable logic array program table. So we have to create, for these 3 product terms, we have to create PLA program table. This is the PLA table for the given example, but I will teach you how to create one from the very beginning. So initially we have to create 3 columns, one for the product term, one for the inputs and the other for the outputs. We have product terms here, so you have to create 1 column for the product term, one for the inputs, one for the outputs. Now we have to fill in these. We have 3 variable Boolean functions, so we have just 3 inputs, and as the variables have already been assigned to them, so A, B and C are the variables, so we just write them in the inputs column. So we have actually 3 other sub columns in the input column. 1 column is for A, 1 for B and 1 for C. If there would be more variables, we would just write them in the inputs column. For example, if there is A, B, C and D, we would just write it here. So we just wrote the input variables in the inputs column. Then outputs. We have 2 outputs, 2 Boolean functions, we just write them here. F1 and F2 are the 2 outputs, the 2 functions, we just write them here. Then we write the product term on the left hand side of the product term. We have a column here, but we just write here on the left hand side of this table. Write these product terms in ascending order, in alphabetical order, but you can write it in any order. It's okay. If you can write BC here, it's not a problem. You can change the order, but it's better to write these product terms in an alphabetical order, just like here. So we just wrote product terms on the left of the program table of the PLA. Now, next, just write or number these product terms. We have three product terms, so we just number them: product term 1, product term 2, product term 3. Obviously, if we write product term BC here, then this BC would become product term 1. So it's okay. Just write them in a specific order. Alphabetical order is better. It's a normal practice. And just number them. The first product term is 1, second is 2, the third is 3. If we had more product terms, then we just number them as like this: product term 4, product term 5, and so on and so forth. So we have 3 product terms. Write them here and just number them in the product term column. So in the product term column, just number these product terms: 1, 2, 3. In the inputs and the outputs, we have to write 0, 1, or dash. For the inputs, look at the product term AB prime, whether these variables, either of these variables, in the normal form, complemented form, or absent. If it is in the normal form, in this term, write 1 under it. If it is in the complemented form, write 0. If it doesn't exist, write dash. 1 is in the normal form in the first product term, write 1. In the complemented form, write 0. C doesn't exist, put dash. Now the outputs column. This product term exists in the function f1, write 1. If it doesn't exist, write dash. AB prime is part of function f1. Yes, it's part of function f1. Write 1. AB prime is not in the function f2. Write dash. If it is there, write 1. If it is not there, write dash. For the inputs, if the variable is in the normal form, write 1. If it is in the complemented form, put 0. If it doesn't exist, put dash. Similarly, for other product terms. Product term AC is in the normal form, C is in the normal form, B is not there, put dash. AC exists in F1, AC is also part of F2, AC is there, AC is there. So we write 1, 1 in front of AC but under F1 and F2. Similarly for the product term BC, we have the product term BC. So in the BC product term, A doesn't exist, put dash. B is in the normal form, put 1. C is in the normal form, put 1. BC is not an F1, put dash. BC exists in F2, put 1. So we have just filled all the rows and columns. But finally, we have to give entries to F1 and F2 also. Whether this F1 and this F2 is in the complemented form or in the normal form. If we have calculated F1 in the normal form, put true or T. If it is in the complemented form, put C. We can also, in the current example, we have represented the two functions in the sum of product form, and F1 and F2 are in the normal form. We could have started with grouping zeros, and that would at the end would give us F1 prime. And similarly, we could do the same for F2. So that would also be the correct approach. And of course, one may ask the question that you are implementing F1 and F2 and not F1 prime and F2 prime. I will show you maybe in the next lecture or at the end of this lecture that we can take the complement of F1 by breaking the fuses in the programmable logical array to make it F1 again. So we would see an example of this, of course, later on. Okay, so F1 in this example is in the normal form, so we just put true, means F1 is in the normal form. It is not complemented. And similarly, F2 is in the normal form, so we would just put true, means it is not complemented. If either of these would be in the complemented form, we would put C. So we have to write T or C between these output variables, T or C. So this T or C means either the value of the values in this row would be T or C. So you can put either of these. So depending on if F1 is in the normal form or complemented form. So in this example, F1 and F2 are in the normal form, so we just write true. means they are in the normal form. Okay, so this is the program table for the two Boolean functions, and now we can look to this program table and can program the programmable logic array, and also we can decide the size or the dimension or the organization of the programmable logic array looking into these two Boolean functions. Okay, so program the logic array. First, we have to decide what programmable logic array do we need. So we have three inputs of this circuit, because we have three Boolean variables, three variable Boolean functions. So we have three inputs, we have two outputs because we have two Boolean functions, and we have three product terms. So we have the values of n, m, and k. N is the number of inputs, m is the number of outputs, and k is the number of product terms. In the current example, it is the value of it as 3. So this is the programmable logic array fulfilling these requirements. We have three inputs, just name them with A, B, and C. We have three product terms, just name them 1, 2, and 3. Three product terms. We have two outputs. For the two outputs, we have two OR gates and of course the fuses. So this is a programmable logic array which has not been programmed yet, but we will program it. We will see it in a while. So this is the programmable logic array, and we can calculate the number of product terms, the number of sum terms, and the number of inputs. We already know them from the two Boolean functions, and also we simplified them, so we got the product terms. Now this combination circuit is not programmed, so we have to program it so that it would implement the two Boolean functions desired. And programming means breaking or keeping some of the fuses here and here and here. So we have to program this programmable logic array. I also write the product terms here just to remind you. The product term number 1 was AB prime, product term number 2 was AC, product term number 3 was BC. Now, this is the programmable PLA program table, and this is the PLA. We have to program this PLA by looking into this PLA table. In this PLA table, the inputs column, the setup inputs column is responsible for programming these fuses. For the product term AB prime, or just look at the variables A. For the product term 1 is keep the fuse to B prime, keep the fuse for A, keep the fuse for B prime, break the fuse. Look at the product term 1, and for the product term 1 in the inputs, this input column is responsible or will tell us how to program these fuses. For the first product term, keep the connection from A, keep the connection from B prime, and break the connection from C. Similarly, we will see how to program later on. Just remember that this column is responsible to program these fuses. The last two outputs columns are responsible to program these fuses, and the final, this row is responsible to program these fuses. So now let's begin with programming. Okay, so here the product term 1 is just I told you, keep the fuse from 1, keep the fuse from B prime because it is 0 here, and break all the other fuses including C. Break all other fuses. So we have connection from A, this is A, so we just keep this connection. We have connection from B prime, this is B prime, this is B prime, and erase or break all other fuses. So we have just kept two fuses, and we have erases or broken all the other links. Similarly, for the other product term 2, keep the fuse or the connection from A, keep the connection from C, break all other connections. Keep the connection from A. So this is the connection from A. Keep the connection from C. This is the connection from C. So keep the connection, these two connections, and break all other connections. Okay. Keep the connection from B. Keep the connection from C. Erase all other. Keep the connection from B. This is B. And similarly, keep the connection from C for C. So this is C. Look at the inputs column. We have 1, 1 under B and C. 1, 1 means keep the connection for B and C. If there would be 0, we would keep the connection for B prime. And if there would be 0, we would keep the connection for C prime, from C prime. So for 1 and 0, keep the connection. But if it is 0, it is complemented. If it is 1, it is normal. Similarly, for the second group of fuses, keep the connection. If there is 1, keep the connection from the product term if it is 1. From the product term 1 and product term 2. For the product term 1 and 2, we have 1, 1. So keep the connection to first OR gate from 1 and 2 and break the other connection. So from product term 1 and 2, which are here, there is 1 for F1, there is 1 for F1 for the product term 2. So from the product term 1 and 2, we keep the connection to sum term 1, that is for F1. So we keep the connection. This is product term 1, we keep it. This is the product term 2, and this is the product term 3, which is broken because in front of product term 3, there is a dash. Similarly, for the other group of fuses, from the product term 1, it is a dash, so break the connection to F2. From the product term 1, it is a dash, so break the connection. Keep the connection for product term 2 and 3. For the product term 2 and 3, keep the connection. From product term 3, keep the connection. So we have just programmed the second set of fuses. Now come to the final set of fuses. It is true, means keep the connection. If it would be complemented, we would just break the connection. So it is T, means keep the connection. Similarly, for F2, it is true, keep the connection. If it would be C, we would broken the connection. If it is C, break the connection. If it is T, keep the connection. So we have kept the connection as it was before because it is T, so we just keep these two connections. So we have now programmed the programmable logic array is according to the implementation table that we have created for the two Boolean functions in the example. So what are the steps? I just repeat the steps for implementing two Boolean functions using a programmable logic array. To implement Boolean functions, first represent them in a truth table or in the sum of min terms form. If they are not in the sum of min terms form, there are different number of ways to represent them in the sum of min terms form or in the truth table. So if they are in the sum of min terms form or in the truth table form, just simplify them using K-map classical map method and represent them in the sum of product form. This is the first step. So the first step is to represent the Boolean functions in the sum of min terms form. After representing the Boolean functions in the sum of min terms form, remove the redundant product terms. If there is a product term in one function and also it is there in all other functions, keep it just once and remove all other occurrences of that product term. So the second step is to remove the redundant product terms. So you would get a set of product terms. The third step is to create a PLA program table, just like this. So we have created this program table by looking into the product terms and depending on if a product term exists in a function or not, and also depending on the input Boolean variables, if it is in the normal form in a product term, if it is in the complemented form in a product term, or if it doesn't exist there. So depending on these features, the Boolean variables are marked here in the inputs either as 1 or 0 or as a dash. Similarly, A product term is part of that Boolean function or not. If it is there, put 1. If it is not there, put dash. So this is a PLA program table for the current two Boolean function example. And then by looking into the two Boolean functions, we decide about the size of the PLA, the number of product terms, the number of sum terms, outputs and inputs. In the current example, we had three variable Boolean functions. So variable Boolean functions means 3 inputs, which is the value of n. By representing the two Boolean functions in the sum of product term, we at the end got 3 product terms. So we had 3 product terms here, 3 AND gates, which is the value of k, and we have 2 outputs or 2 Boolean functions. So we had 2 sum terms and 2 outputs. And then by looking into this program table, we programmed this programmable logic array. We just broke the link from the input variable if it is not if there is no 1 or 0 under it. So we just did not connect that variable in its complemented form or normal form. For example, product term in front of product term 1, A is 1, B is 0. So we just kept the connection from A and we kept the connection from B prime, and we just erase all other connection. So this way we programmed the programmable logic array that we had decided. So this combination circuit is a programmable. This combination circuit is a PLA which has been programmed for the two Boolean functions implementation. Okay, hope programmable logic array is now simple to design for your specific Boolean functions implementation. Please refer to the book Digital Logic in Computer Design by Maurice Manu, and also please read the presentation slides I have shared. If there are queries that you have observed during watching this lecture, please keep a list of those queries which you can ask during the online session. Thank you.